Good afternoon, guys, gals, and non binary pals, or whatever time it is for you that are watching this now. So, we're going to do week 2 today. We went over a few things in the past week. I think we hit chapter 1, section 1, 2.4, 2.5, and then the first few sections of chapter 3. So, chapter 1 is all about slopes and equations of lines. 2, we touched on exponential and logarithmic functions. And 3, we did some derivatives, rates of, well, not derivatives yet, rates of change. So I don't want to spend too much time talking about the concepts of everything because there's a lot of problems that I want to get done. We're going to go over some of the quiz problems that people had trouble with, a couple homework problems, and you'll kind of see the concepts explained there. So one thing I'm going to try in this video is that I'm going to try to put time tags on it. So if you want to see a specific problem, you can go to that point. It'll show up on the bar in the bottom of the video, I believe. And you can just click on that time tag so you don't have to watch the whole thing or try and dig through the whole thing. So without further ado, let's go ahead and do some problems. So, I believe the first one that I want to do, let me check my notes. Yeah, so this one I think was on your quiz, possibly. This is from chapter 1. It says, so this is 1.1.29. It says, find an equation for each line in the form ax plus by equals c, where a, b, and c are integers with no common factor. And a is non-negative. Okay, and then they say, they give us this information. They say the line is through negative 4, 6, and it's parallel to this line, which they give in the same form. Okay, so basically, we're going to find an equation for this line. The easiest way to do this is, right now in my mind, it's point-slope form. So recall that point-slope form, remember you have generally two ways of writing a line, and that's point-slope form or slope-intercept form. So point-slope form is y minus y1 equals m times x minus x1. And this needs, you need two things to be able to find this. And that's, you need a slope, m, and you need a point, which is our x1, y1. Okay, well, we have a point, so we already know this is going to be negative 4, 6. We just need any point on the line. So we might as well use the point they give us. But now we need a slope. So in order to do that, we should think to ourselves, when we see parallel, that means same slope. So we look at this line up here. We think same slope. So if we can find the slope of this line, then we can find the slope of the line that we have. So how do we do that? Well, let's just put it into slope-intercept form, where the slope is very easily visible to us. So in order to do that, we're going to solve for y. So I'm going to subtract 3x from both sides. I get 13 minus 3x. And then I'm going to divide by 2. So 13 halves minus 3 halves x. So the term in front of, should be a little bit more clear. This number out in front of x, that's the slope of that line, right? Because slope-intercept form is, let's write it in red. So remember, slope-intercept form is like y equals mx plus b. Only here, so whatever term in front of x, that's the slope. So that's what this is. Okay, so we know that the slope of this line is negative 3 halves. That means the slope of our line is negative 3 halves. So now we know that our slope is negative 3 halves, and we have a point, negative 4, 6. So we can just plug the rest into the point slope form. So we go y minus y1 is 6, then our slope, that's m, and then x minus x1, which is negative 4. So remember, this is, let's just write underneath what everything is. Here's y minus y1. This is m. And this is x1. Probably get rid of this. Okay, so those were those are the things we needed. All right, so let's simplify this up a little bit. Let's move this over. So if I can, if I distribute, first of all, this minus a negative on the inside becomes a positive. So let's just write that quick and get rid of this parenthesis. This is x plus 4. Now I distribute. I should have minus 6 here. Now I'm going to add 6 to both sides. I might even be able to finish or fit this all in here. So adding 6 to both sides gets rid of that 6. So I have y equals negative 3 halves x. And now I'm going to multiply by 2. Why do I multiply by 2? Well, I guess I don't have to do it now. So let's do this first. Let's add 3 halves x to each side. So what this does is it gets it in that form that I wanted from earlier, right? So if we remember, we wanted a line ax plus by equals c. Now the last part of that is a, b, and c are integers. Right now I have my a is 3 halves, so I have to multiply everything by 2. So I have this, 3 halves x plus y equals 0. This is not an integer. So I'm going to multiply each side by 2. And I'm left with 3x plus 2y equals 0. And that's your solution. Okay, so we're going to do a couple other problems from this section. And it's pretty much the same concept. All it is manipulating point slope form and slope intercept form. So let me see here. Let's do... I was going to do number 19, but I think I can probably skip that and just do number 36. So it's a little bit more interesting. Okay. So this question says, find K so that the line through the point 4, -1, and K2 is, first we want to find it if it's parallel to 2x plus 3y equals 6. And then we want to find if it's perpendicular. Sometimes I'll write this. That's the symbol for perpendicular. To 5x minus 2y equals -1. So both of these are going to involve a slope. Parallel means same slope. Perpendicular means the slope is a negative reciprocal. So basically what we're going to do is we can find the slope just by if we're given 2 points, we can find the slope just given those 2 points. So we're going to use that formula and then set it equal to the slope that we get from part A, and then we'll set it equal to the negative reciprocal of the slope that we get from part B. Okay, so part A. Let's just again recall slope of a line given 2 points. And those points will be x1, y1, x2, y2 is given by, we take the rise, so the amount we go in the y direction over the run, which is the amount that we go in the x direction. So some people like to think about this as rise over run. Okay. So now what we're going to do is we're just going to, first we're going to find the slope to the line they give us. And then we're going to use this equation. Okay, so let's find the slope of 2x plus 3y equals 6. And how do we do that? Well, we're going to do that the exact same way that we did that in the last problem, which is put this thing into slope-intercept form and then figure out what number is in front of the x. So again, we're just going to start here. 2x plus 3y equals 6. I'm going to subtract 2x from each side. 3y equals 6 minus 2x. And then I'll divide by 3. 3 equals 6/3 minus 2/3 x. The only thing, I could simplify that 6/3 if I want, but it doesn't really matter because the only thing I'm after is this negative 2/3. All right, great. So we have the slope. Now we're gonna, you'll see what we do here. So we have these 2 points, 4, -1, and K2. So I'll write this up here. Let's do 4, -1. That's going to be our x1, y1. And K2 is our x2, y2. Okay, so now we just do that equation that I showed you. So we do y2 minus y1, that's 2 minus -1 over x2 minus x1, which is k minus 4. This is equal to 3 over k minus 4. And now we're going to set that equal to this slope that we just found. So we know that this is an equation. This thing on the left is an equation for the slope of the line, but we also know that the slope of that line is equal to negative 2/3 because it's parallel to this line that we just figured out what the slope was. So basically the idea now is to just find the right k. And how we find the right k is just by solving for k like we would in any other equation. So there's something we can do. We can just, let's call it cross multiplying. I'm sure you've seen it before. So we have 9 on this side, and then 2 times, or negative 2 times k minus 4 on this side. Let's see here. How do we want to do this? Let's move this down. So that gives us that. Next page, we're going to divide by negative 2. This is k minus 4 here. And then we'll add 4 to the other side. So this is negative 9 halves plus 4 equals k. And once you do that math, so I guess I'll do it the first time, and the second time I won't. So least common denominator is 2. And then we just add across the top. We have negative 1/2 equals k. This is for part A. Okay, cool. Now let's do part B. So our line this time, let's just copy this whole thing. So this is what we want. So what this means is that we're going to find the slope of this line, and then we're going to flip it and negate it. That's the negative reciprocal. So just like the last time we did this, start here. Subtract 5x. So negative 2y equals 1 minus 5x. I'm going to divide by negative 2. So be careful that we bring that negative over. All right, so now here my slope is 5/2. And then I want the negative reciprocal. So that means I flip it. That's the reciprocal part. So I get 2/5 and then negate it. It's negative 2/5. Okay. So at this point, I think you can probably guess what the next step is. We already know what our slope equation is. That's not going to change. We know it's 3 over k minus 4 because we're using the same 2 points, remember. And now we're just going to set this equal to negative 2/5. So the thing on the right is the only thing that's changed. Again, we'll just cross multiply. And now I have 3 times 5, so this is 15. Equals negative 2 times k minus 4. Dividing by negative 2, I have negative 15/2 is equal to k minus 4. And then I'm going to add 4 or 8/2 to each side. And I will have negative 7/2 is equal to k. And I'm done. So the only thing that really changed in this problem was, I mean, I guess the lines were different, but conceptually the only idea was that you had to know that it's the relationship between your line and a line that is parallel to it, and then a line that is perpendicular to it. So if you have another line that is parallel to your line, your slopes are the same, like we did in the first problem. But if it's perpendicular, the slope is the negative reciprocal. All right, let's keep going. Let's see if I have a problem from chapter 2 or not. Nope, I don't. So, yeah, so when we do these, Tyler and I, we look at the homework and we look at the quizzes and we see where people had the most issues. And so for this quiz and this homework, we had really not many people with issues in Chapter 2. We did have a fair amount of issues in Chapter 3, though. So that being said, it's not that nothing in Chapter 2 is worth your time, because it definitely is. But if you want to see some of it, or if you have questions on it, you should contact one of us personally. So remember, I still do office hours by appointment. I had one student come the first day of office hours, and I haven't had anybody since. So this is what I'm here for, to help you out. Feel free to use those when you want. All right, I'm off my soapbox. Let's move on to Chapter 3. So Chapter 3 is about limits and rate of change. Chapter 3, at first, it brings up the idea of a limit, so the first section. And I think a lot of people struggled with this, particularly this question we're about to do. So I am going to go over a little bit of the concepts as we go. So we'll see how that goes. So 3.1.3. So this is 3.1.3. So we're doing limits. Here's the question. It's actually a multiple choice question, but there is some stuff to be said about it. So if limit as x approaches 4 from the left, that's what that means. That's equal to the limit as x approaches 4 from the right, and those are both equal to 6. But f of 4 does not exist, then the regular limit as x approaches 4 of f of x blank. And then the options are A, does not exist, B is 6, C is negative infinity, D is infinity. Okay, so the punchline here is I'm not really gonna show you. I'm not going to do the work first, because this question doesn't really involve any work, actually. It's testing your knowledge of if you know what a limit is, or if you know what a limit means. So we don't really have to draw this, although I'm going to, just to kind of illustrate a point. But first, I'll give you the answer first, and then we'll go over what limits are and why they are the way they are. So the answer is B. The limit is 6. So first, let's draw the picture. You might ask, well, how do I draw a picture? I don't know what f is. That's right, you don't know what f is. But you don't really need to know what f is. We can just draw something that we think could look like f, and it'll apply either way. So what do we know about limits? So this is saying, so if I'm going to draw, let's start drawing f here. Not quite like that. Let's do this little dotted line here. All right, so what this is saying here is that the left limit as x approaches 4 of f is 6, and that the right limit, maybe it's up here, is also 6. Right, so this is the way that I think about this, is it's kind of like in two sections. So let's draw like a little arrow here. Maybe an arrow here. So this part is saying that the limit as x approaches 4 from the right of f of x is equal to 6. And this part is saying the limit as x approaches 4 from the left of f of x is equal to 6. Right, so we can imagine like a little x down here or over here. And then the f of x is what we have here. right, for any given point. So what it's saying is as you get closer to the 4 on the bottom over here, you get closer to 6 over here. Okay. So in this case, I drew a hole there. That's what we mean by it doesn't exist there. You will also find that some people will say, this is kind of a technical note that you shouldn't get wrapped up in. But 1 over x, for example, doesn't exist at 0, but it doesn't have a hole there. What happens is the function kind of blows up. And we don't really say that it doesn't exist. It's not actually defined there in the first place. So I don't know. It's a bit of a long road you can go down. But these holes are important. So I want to talk a little bit about limits in general. So we're going to talk about one-sided limits and two-sided limits and how they're related to each other. And because this is how you do this problem, essentially, is by knowing the relation between one-sided limits and two-sided limits. So let's take a little break. So we already figured out the answer to the problem. So let's do a note on limits. Okay, so start with one-sided limits. So one-sided limits are either approaching one-sided limits are either approaching from the left or the right. So if we have one from the left, we could do, let's just give our two examples here. We had this one over here. We'll just copy paste this thing. So we'll put a hole here. So this is the one we just did. So here's what we mean. So here's from the left. And then here's from the right. And we denote, so notice that, so in this concept, right? So the concept of a limit in the first place is we're talking about the reason a limit is useful is because we can talk about points that don't exist on functions, like this hole in this function. We can talk about what we think it would be. We can get so close to that point that we can almost pretend the point is in the function. So if you're looking at this function up here, for instance, and you're saying, well, I really want to know what f of 4 is, but f of 4 doesn't exist. Say this is a graph of whatever you want it to be. Then, what we can say is, well, we don't know what f of 4 is because f of 4 doesn't actually exist, but we can get you so close to f of 4 that the amount that by which we're wrong by, it'll be negligible. So basically, it's an estimate, but the estimate you can make as small as you want. So that's the whole point of limits. We denote, so left has a minus, a left-sided limit has a minus sign, and a right-sided limit has a plus sign. And then the regular limit, the regular old limit word, is actually just it's a two-sided limit. So it means both of them. So by definition, a two-sided limit exists only if, so if and only if, both of the one-sided limits exist, and they equal the same number. So what does this mean, if and only if? So this is a math term. You don't really need to know the exact logical definition of it, but I'll tell you what it means in this situation. So this means what? So if we have that both one-sided limits exist, so if both one-sided limits exist and are equal to the same number, we're going to call that number M. Then the two-sided limit or just limit also exists and is equal to M. Oh, that's an awful M. M. All right. But it's not just that, it's the other way around too. That's what that highlighted mathematical statement that I showed up there, it's pretty powerful. So it also means that if the two-sided limit exists, so if the two-sided limit exists and is equal to M, then we know that the both the one-sided limits exist, and they are both equal to M. So this is kind of the big takeaway here. This right here is what we had to know to do our problem. So our problem gave us that both one-sided limits existed and they were both equal to the same number. So knowing this fact here, we should be able to say that the two-sided limit exists and is also equal to that number. So this is everything. Now the other fact is also just a useful piece of information for you to know. That's really all I wanted to say on limits in this respect. If you want tips for so evaluating limits, see page 140 in your text. This is like the table. I don't have to write that. This is basically the table. So if you watched last week's video, I wrote down all of the tables that you should know for the review, all of those mathematical properties, the rules basically. Page 140 gives you the rules for limits. So if you have any doubts, it's very easy to just say, oh, limits work just like I want them to. Limits work just like, multiplication or whatever. They have all these nice properties. But there are a few things that you have to kind of be careful with. So it's good that you know them. It's not something that you should just take for granted. So check that out. Write down the ones that you need to know that you don't already know and use them. All right, so let's move on to the next section. So this was a quiz question, and the next, I think we have 2 questions left. They are both also going to be quiz questions. So I believe that gives us 4 of the 6 questions that we've covered are from your quiz. So this is, we need this, 3.2.27. It says find the value of k that makes the function continuous. All right. So what is continuity? So I don't want to go too far into it. But in simple terms, a function is continuous if you can draw it without picking up your pencil. There is a better, more rigorous definition probably in your text, if not in other texts. But this should be about all you need to know. So we're given this function here. For x minus 3, and then kx minus 1. So this is what's called a piecewise function. What that means is there are 2 pieces to it, 2 or more pieces to it. So it's a little bit more complicated looking than some of your other functions, but it's really not, it really shouldn't be anything that's super intimidating. So the first part, it's this thing here. This part is a rational function, so it's continuous everywhere its denominator is 0. So everywhere except where its denominator is 0, excuse me. Yeah. So in that case, that's where x equals 3, right? So that's why this piecewise function is introduced. It's saying, well, you know, this whole thing is continuous wherever x doesn't equal 3, basically. So we need to fill in this gap, right? There's this there's spot where it's not continuous. So if we plug in something there, then we'll make it continuous again. So that's what this function is here. That's what this is an attempt to do. And then they say, okay, well, what value of k do we need to use to make this to make it plug in the right hole, right? So one thing to do. So let's try to draw this kind of. Again, this is something that we're not really going to know how to draw, but also it really doesn't matter. So let's say here's 3, and then we have this hole right there. So this is not defined at 3. So let's just draw this, and then maybe it goes up like that, or something like that. And then we want this point here, right? And we want it, so it's got to be kx minus 1. But depending on what k you pick, so let's say that x is 3 here, right? So if you picked, if you pick k to be 3, then you could get a function value of 8. Or if you picked it smaller, you could get one of 6. Or maybe if you picked it too small, you could be down here, right? So we want to pick the right k. Well, how are we going to pick the right k? Well, this is kind of what I alluded to earlier. We don't know what the function is at 3 because it's not defined at 3. But what limits allow us to do is to figure out what we think the function should be. So if we take a limit here and we say, okay, well, if these limits match up, which they should, then we can just figure out what the limit is and then plug that point in, and then everything will kind of complete itself. So that's exactly what we do. We're going to look at the limit. So, and we're taking a look at the limit of the first part of the function. So we want the limit, and we're going to 3, and we want our function that isn't defined at 3. Okay, so we want to find this limit, and then maybe we can figure out what point we need to use, and then that'll get us one step closer to where we need to be. Okay, so evaluating this limit, the first thing you always do generally is just plug in the number. That's probably not going to work here because our function isn't defined there. We'll see why in a second. But let's just plug it in just because. And then we have 3 minus 3 here. Now if you notice, this is 18, and this is minus 18. Let's write this in blue. So 2 times 3 squared is 9. So 2 times 9 is 18. And then I have minus 3 minus 15. That's minus 18. And then this is 3 minus 3. Which is, so this is 0. And this is 0. So this is no good. So we have to do something else. Generally, the first thing I think of is, can we rewrite it? Can we rewrite it in a way that'll make it nice? So the first thing that, when we think of rewriting it, we should think of is factoring things. So in my head, I'm going, can I factor this, right? This is a rational function. There is a polynomial on top and a polynomial on the bottom. So chances are, if I can try to factor this out, I might get terms that can cancel. Right? Now, if this was just a polynomial, there wasn't anything on the bottom or on the top, then factoring is going to make it look nicer, but nothing's going to cancel because I'm not dividing by anything. Of course, I also wouldn't run into the problem of being undefined. So, tomato, tomato. What we're going to do then is factor it. So I know that I'm hoping there's an x minus 3 term in the polynomial on top because that's what I want to cancel on the bottom. So I'm going to put that up there, and then I'm going to see if I can think of what the other piece would be. So this is kind of like, you're kind of like, you have like a premonition or something, right? You're kind of like looking into the future and you're saying, okay, well, it's only going to be useful to me to factor this if I can get an x minus 3 out of the top. So I'm just going to put it there and then see if I can find the other factor and it works out. So let's see, if I need a minus 15 and I have a minus 3, so that means I need a plus 5 here. And then I have a 2x squared, so that means I'm going to need a 2x there. So let's just check. So let me erase this stuff here. So let's just check this. Is this what we want it to be? I have 2x squared plus 5x minus 6x minus 15, 2x squared minus x minus 15. That's exactly what I wanted. Okay, cool. Well, that happened to work out. So what we can do then, cancel that, and we just have the limit as x goes to 3, or as x goes to 3 of 2x plus 5. And now we can just plug 3 in, get 2 times 3 plus 5, and that's 11. Okay, so that means that we know that the function value at 3 should be 11. So we're not quite out of the woods yet. Remember that at 3 the function is kx minus 1. So what this is saying is at 3 we need this to equal 11, right? So and we know that the limit as x goes to 3, g of x is equal to 11. So what this tells us is that we want kx minus 1 to equal 11, but since x is equal to 3 here, this actually means is k times 3 minus 1 is equal to 11. So now we just do some algebra, add 1 over to each side. We have 3k equals 12, or k equals 4. All right, that's it for that problem. So this is our last section now, and we're going to deal with average rate of change. So average rate of change is, well, this is kind of like a concept that's going to be really important for everything we do in calculus. So limits are also very important. They're important for all analysis, and they're kind of like the building blocks for average rate of change. And everything that comes afterwards. So average rate of change, that's super useful. So let's just kind of go over that. So we have average rate of change. This is between 2 points. You have f of b minus f of a over b minus a. And if you notice, that's the same as y2 minus y1 over x2 minus x1, which is the slope. So here we have some picture that looks kind of like this, and like this. I have a point A, I have a point B. Great. So here's my f of A. My f of b. All the way around. That's kind of, I think it's right there. Okay. All right. So what we're really just doing is finding the slope between those 2 points. But there's another idea. They say, okay, well, that's great. I can find the rate of change between these 2 points, but what if I wanted to find the rate of change at just this point? So let's call this f of a. Right? So this is called instantaneous rate of change. So this is like if something is, let's say that you're accelerating in a car, right? What if I wanted to figure out how you were accelerating at any split second, like what your exact acceleration was? Well, the idea of a limit allows us to do this. So what we do is we take the average rate of change. So here's a plus h. This distance here is h. And now what we're going to do is we're going to bring h. So we obviously can't just be equal to a because we're going to have 0 over 0. But we can bring h really close to 0. What this is saying is we can bring the points really close together, so close as we want, so that the difference is negligible. And that'll give us really what is an idea of instantaneous rate of change. So this is instantaneous rate of change. You take h to 0. And then it's the same formula. It might look different. So you have f of a plus h, or minus f of a. And you have h. But notice this really is the same thing. Because here's my f of b. This f of a plus h is taking the role of f of b. And if I were to plug in a plus h for b, so notice, let's just write this. So f of b minus f of a over b minus a. We're going to set b equal to a plus h. Then I have f of a plus h minus f of a over a plus h minus a. These cancel. And I'm left with this thing here, or not that thing. I'm left with this thing. Okay. It's a very important concept in calculus. So as you might have seen earlier, my Apple Pencil is dying. We have one problem left, and I think we can get through it. So let's try it out. It's using instantaneous rate of change. So this is 3.3.17. This is another quiz problem. We have g of t equals 1 minus t squared, and we want the instantaneous rate of change at t equals negative 1. So we're going to do this by definition. So one thing that I forgot to write up here, but the idea is definitely that we're going to be taking a limit, right? Like I said here, this is the limit. This means the limit as h goes to 0. So by definition, we're just gonna go down the line here. So the instantaneous rate of change is the limit as h goes to 0 of g of t plus h minus g of t all over h. And I'm going to copy this because I'm going to be pasting it a lot. This is equal to, now we're going to plug it in, 1 minus t plus h squared minus 1 minus t squared over h. This is equal to, let's just paste all these right now, huh? That, maybe 3 more. That might be enough. All right. So we FOIL this out. We get t squared plus 2th plus h squared minus 1 minus t. Well, we can distribute this now. So distribute that negative. And now we're going to distribute the first negative. So we have 1 minus t squared minus 2th minus h squared minus 1 plus t squared all over h. And we notice that some things cancel. This 1 and that 1 cancel. This negative t squared, that t squared cancel. And now notice we have a factor of h left over in the top. So negative 2th minus h squared over h. If you're doing instantaneous rate of change, this will always happen because you need that h on the bottom to go away. So we're going to cancel out the h's. So I have, this one's gone, one of those is gone, and that one's gone. I'm left with negative 2t minus h. And then just plugging in h equals 0, I have negative 2t. So then instantaneous rate of change at t equals negative 1, well, you just plug in negative 1 for t. You get 2. Okay, that's it. We made it. Made it before my pencil died. If any of you have any questions on this stuff, please set an office hours appointment with me, or you feel free to email me. Otherwise, hope you have a great weekend. Good luck on your exam. Bye, everybody.